So our second skill in our kinetics unit is on rate law, reaction order, and rate constants. So one of the things that we really have to make sure we understand well is what a question is asking us. So let's go ahead and review some of the content from our first skill, which was on writing rate expressions. So writing rate expressions has to do with relating the rate of the reaction to the rate of appearance of either products or disappearance of reactants. So when we had our generic chemical equation here and we wrote a rate expression, we could, again, use either reactants or products, and that's going to be a difference when we move on to today's skill. But we used coefficients from our balanced chemical equation to become part of the rate expression. That's going to be something else that's different from things that we talk about today. So we learned about rate expressions, both writing and using rate expressions in our last skill. And then we talked about what reaction rate was, right? It's a change in the concentration of either reactants or products as a function of a change in time. And we talked about the three different ways that we think about rate. An average rate, which is really over a certain time span, or an instantaneous rate, which is a snapshot in time. That's where we draw that tangent to our line in order to figure out what that rate was at that instant. And then a special kind of instantaneous rate, which happens right when the reaction starts. That's right out of the gate. We call that an initial rate. That's going to become an important rate that we'll talk about in today's skill. So we measure reaction rate and we graph it experimentally, and then we can use that information to answer some additional questions. So that's kind of reviewing from last skill. So today's skill is all about what we call a rate law, or sometimes referred to as a rate equation. And this expresses the rate as a function of concentration, not change in concentration, concentration. So for any generic reaction that occurs at a fixed temperature, so that's really important. This is going to be something we'll revisit in our fourth skill here. Reaction rates are temperature dependent, okay? But if we take the same generic reaction and we write not a rate expression, we write a generic rate law, that's what this looks like. We say rate equals rate constant times the concentration of a species raised to a power that we call the reaction order, okay? And it's only reactants. So a couple of things that highlight that this is different from our rate expression, okay? Rate laws are only expressed in terms of reactant concentrations. You'll notice that C's and D's do not appear in our rate law. Rate laws do not have anything to do with product concentrations. In addition, these exponents that we have, the M and the N, are intentionally written as different letters to remind us that we do not get them from our coefficients in our balanced chemical equation. So two big differences between what we write as a rate law and what we wrote last skill as a rate expression. Both of them are equal to rate, and that's going to become important in our next skill. But rate equals rate constant times the concentration of a reactant raised to a power that we call the reaction order. So highlighting this little k, this rate constant, we saw that in our last unit on nuclear chemistry, when we talked about first order reactions that were nuclear decay processes, we talked about a rate constant. These rate constants are really proportionality constants that allow us to relate the change in rate as a function of a change in reactant concentration. Okay, these are reaction and temperature specific. Okay, these rate constants, as the name implies, they're constants. They do not change as the reaction proceeds, but as the concentrations of our reactants change, so does the rate, and they change so in proportion to the rate constant. Okay, what is this whole process and this thing with reaction order, these M's and these N's? Okay, these are a reflection of how the reaction rate is going to change as a concentration of a given species and how that changes. Okay, so highlighting, we're going to have three options for those M's and those N's. They can either be 0, 1, or 2. Okay, so let's take the first order process just because that's what we dealt with our nuclear decay processes. They were first order processes. First order basically just means that our rate is going to double when the concentration of a species that is first order doubles. Okay, and we'd say that it's first order with respect to that species. Okay, so it's almost like a one-to-one sort of relationship. We double the reaction concentration, we double the reaction rate. We triple the reaction concentration, we're going to triple the reaction rate. That's first order. Second order, it really means that this M or this N is a 2. It's a square. Okay, meaning if we double the reaction the reactant concentration, we quadruple the rate. We triple the concentration, we 9 times increase the rate. Okay, so it's a square relationship. Zero order, and it seems a little bit counterintuitive, but this means if I change the concentration, I don't affect the rate. So if I double the concentration, the rate doesn't change. Triple the concentration, rate doesn't change. Okay, that's zero order. Okay, we're going to see how this kind of plays in mathematically in a minute here. All right, so one of the skills that you're going to need to know how to do is how we write a generic rate law. We already kind of said this. Rate equals rate constant times the concentration of reactants raised to powers that are reaction orders. Okay, and we don't get those from coefficients. Okay, and so again, if we are writing something that's generic, we're going to keep these as variables. Okay, I shouldn't say these coefficients. We're going to keep these exponents. Let me fix this here. This is exponents. So keep those exponents, which are not coefficients from your chemical equation. Keep those as variables. Okay, so whatever your reaction is, take your reactant concentrations, raise them to powers that we're going to keep as variables. That's how we write a generic rate law. All right, so how do we use a rate law? What are some problems that you're likely to see that have to do with rate laws? Let's say that you were given a specific rate law. Kind of a simple qualitative equation or question you might get is, well, what's the reaction order of A or of B? You're basically just going to look at this exponents, and I keep writing coefficients here. You're going to be looking at the exponents here. Okay, determine reaction order by looking at the exponents. Okay, it is first order with respect to A if this exponent is 1, second order with respect to B because that exponent is 2. Third order overall, we add all of the exponents together, and that's going to give us that overall reaction order. Okay, so you're just looking at the value of the number that is the exponent. Is it a 0, a 1, or a 2? And that tells you the reaction order. So that's kind of the simplest version or flavor of using a specific rate law to answer some questions. You also might have to do a little bit of math here. Maybe you want to determine how the rate changes with changes in concentration species, right? So to do that, you're basically going to put in whatever factor you're changing the concentration by into this expression, this rate equation, and then you're going to see what happens. So let's imagine here, because we are first order with A, if I'm going to double my concentration of A, I can see that mathematically, I'm going to double my rate, right? 2 to the first power means I'm going to have a 2 times my rate in order to maintain that equality. Okay? If I put in a 2 for my B, right? 2 squared is 4. That means my rate is going to be 4 times. If I put a 3 in, 3 times my concentration for B, that means I'm going to have a 9 times my rate. Okay, so those are some of the relatively simple qualitative or semi-quantitative questions you might see about using a specific rate law. All right, so now let's talk about the kinds of experiments that you're going to do in lab, the kinds of calculations we're going to be doing in lecture that have to do with writing a specific rate law. All right, so what do we mean about specific? That means we are specifying these values for our exponents, right? We are going to be determining what those exponents are, okay? And again, how we do this is we need to have some pieces of information. We actually need to do some experiments to get initial rates. Remember from our last skill, that was looking at the instantaneous rate when time equals 0. We know how we can get that from graphical data, but how we're going to start with most things for what we'll see in lecture here is you're going to get a table of data that has initial rate information. Okay, so we know how we obtain it, right? We learned that from last skill. You're actually going to do that in lab, but we're just going to talk about how we actually use that data. To write a specific rate law, we need to actually figure out what these values of M and N are. This is what we call the method of initial rates. We're going to talk about how we do that in the next few slides here. The last piece of having a specific rate law is you actually need to calculate what the rate constant is. Now follow with me here for a second. If we have the rate data, we have a table of rate data, we use that rate data to calculate what these exponents are, then the only variable left in this equation is k. So we'll be able to solve for what that is. Okay, so that's kind of what it means to write a specific rate law. We're going to go through and practice how you do that. Okay, so this is kind of a flow chart for how we'll do this process. We're basically going to often not have this part. We'll be actually starting with a table that has these initial rates. But just to highlight, these came from experiments where you were plotting concentration versus time, getting the slope to determine initial rate. You're going to do that experimentally in lab, but when we do stuff in lecture here, we're going to be starting with a table of data that has initial rates. All right, so now what do we need to do with it? We need to compare initial rates of different experiments, holding one variable constant, one concentration constant, while we change another one, and we see how that affects rate. Okay, that's going to give us our reaction orders. And just like we talked about on our last slide here, once we know the rate and we know the reaction orders, the only variable that's left is our rate constant. All right, so let's go through and let's practice this. We're going to have a generic reaction here. This is going to be A plus 2B goes to C plus D. Okay, so what we're going to do here is to determine the reaction order, we need to have a bunch of experiments that allow us to have one reactant concentration that we hold constant and then another one that we're going to change. So maybe you can see this already, but we're going to explore it a little bit more on the next slide. If we compare, for example, experiments 1 and 2, we can see here's the reaction rates for each of those experiments, but I keep reactant B concentration the same, and then I change reactant A. So comparing experiments 1 and 2 are going to allow me to determine the reaction order with respect to A. That's the one that's changing. I'm going to determine the reaction order with respect to that. So this is going to look a little bit crazy here, so bear with me on this slide to understand how we're going to do this. To determine reaction order, we need to compare two sets of data, two experiments, okay? We're going to have one reactant that we hold constant, and then we're going to be changing another one. So for this first set, let's imagine that we're changing and comparing experiments 1 and 2. Looking at this, I can see that I'm going to keep the reactant concentration of B the same, and I'm going to be changing reactant concentration A. So one of the things I need to ask is, well, what is the fold factor change in concentration? I'm going to call this C. So I can look at this and I can see that my value for C here is going to be 2. I've doubled my reactant concentration. Then what I need to do is go over and see what was the corresponding change then in the rate. What's the fold change in the rate? Looking at these numbers, I can see that that also changed by 2. I doubled the reactant concentration, I doubled the reaction rate. We learned before that means it's first order. Mathematically, what you can do is look at this equation. Okay, let me even highlight this. This is a really important equation here. I'm solving for x. What is the exponent that I need to put in there so that the fold factor change in concentration is equal to the fold factor change in rate? 2 to the x equals 2. My x must be equal to 1, right? Hopefully that makes sense there. Let's go through and let's compare another set. Now we have to be careful what we compare, right? If I compare 2 and 3, If I compare reactions 2 to reaction 3, well, okay, I'm changing the concentration of A, but I'm also changing the concentration of B. I'm not going to be able to determine. There's too many variables that are changing there. I can't kind of compare that one. I need to find one where I'm changing the concentration of B, but I'm keeping A constant. How about this guy, right? If I am looking at comparing these, if I compare 2 and 4, I can see that I'm doubling the concentration of B, but I'm keeping the concentration of A the same. So it's really important to go through and identify places where you keep one reactant concentration the same and you change the other. So again, I'm going to come over here and I'm going to say what happens to my reaction rate. That's also a 2. So that means that it's first order with respect to B. Okay, so this one was pretty straightforward. We could just kind of look at those numbers and see that they were a factor of 2. But I'm going to highlight an important equation here. If you don't have easy numbers to work with, you can actually figure out what that fold factor is, what that exponent is, by taking a ratio of the log of those numbers. So the log of 2 over the log of 2 will give you what that x is. Now again, that one was pretty easy because we could see the relationship there. But if you have real experimental data where maybe the numbers aren't whole numbers, you might need to use this. That equation will be provided for you. Okay, so now what we have here is we know that we can do a little bit more by writing what our rate equation is. We know that it's first order with respect to A and first order with respect to B. If there's ones there, we don't tend to write them as exponents. So we have a little bit more of a refined rate law that we've defined the values of M and N there. First order with both, so this is second order overall. The last little piece here is saying, you know what? Now we've got one unknown. I'm going to pick one experiment here, and in theory, you could pick any one of these 4 experiments. In reality, you'd probably want to do this calculation with all 4 experiments and then take an average, but I'm going to show you what we do here. I'm basically going to take this rate value, put it in for there, this concentration for A, this concentration for B, and I'm going to solve for K. Okay, so that's what I'm going to do here. I'm going to say 1.75 times 10 to the minus 3. Let's look at what the units are here. This is going to be moles per liter per second. Okay, that's going to be equal to my rate constant times my concentration of A is 2.5 times 10 to the minus 2 molar, and then 3 times 10 to the minus second molar. So I'm solving for my unknown, right? This is my unknown. That's what I want to solve for. But more important than figuring out the mathematical answer to this, the numerical piece, I want us to take a look at the units. So let's go ahead. The math works out that this value is 2.33. But let's see what the units are. All right, I would have had moles per second and then over moles, or I should say molar times molar. Okay, take a second, pause if you need to, make sure that you can see that that's what those units are. One of these molars is going to cancel, and I could take this second and put it down in the denominator there. So the units of my answer are going to be reciprocal molar, reciprocal seconds. Okay? So one of the things that we're going to see is depending on the overall order of the reaction. This was second order overall, which meant we had 2 molars on the right. Depending on how many molars we have over on the right is going to determine how many molars we'll have there, which determines the units of our rate constant. Rate constants have different units depending on the order of the reaction. Okay. So again, writing a specific rate law is going to have all of these pieces. So putting this all together, rate equals rate constant times the concentration of A times the concentration of B. These were both first order. And then we want to report what the rate constant is. 2.33, and then it's molar, reciprocal molar, reciprocal seconds. Okay, so that is the specific rate law for this experiment that was based on the analysis of the experimental data.